Now that we know a little bit about the hyperbolic functions, how they're defined, I want to spend this video discussing some identities with the hyperbolic functions as well as the derivatives of the hyperbolic functions. So we have this whole new set of functions, the hyperbolic functions, sinh, cosh, hyperbolic tangent, and all their reciprocals. And here is just a quick reminder in this box of how they are defined. Remember that they are defined as combinations of the exponential functions, sinh and cosh are hyperbolic sine and hyperbolic cosine. I'm saying sinh, that's kind of the shorthand way to describe it. And then, of course, the other four hyperbolic functions are defined in terms of the hyperbolic sine and the hyperbolic cosine. So we spent some time looking at the graphs and talking about how these are related to hyperbolas on the last video. So on this video, I want to talk about a couple of identities. So I'm going to list out all the identities, but let's go through two proofs here first. So it turns out that the hyperbolic sine is odd. So let's actually prove that. So what it means to be odd, just as a quick reminder, is that f of negative x is equal to negative f of x. So that's what we have to prove for the hyperbolic sine. So these are kind of fun, quick little proofs, so let's just do them. So this is going to be, so let's take it. So if f of x, take our hyperbolic sine, if f of x is the hyperbolic sine of x, then f of negative x would be the hyperbolic sine of negative x, which would be, in its exponential expansion, let's get it up there in case you don't have them memorized yet, it would be e to the, we'd plug in a negative x for x, so it would be e to the negative x minus e to the negative x all over 2. Okay, so well, let's just simplify that a little bit, and we're going to have e to the negative x minus e to the positive x over 2. And if we factor out a negative 1, because we're trying to prove that this is the opposite of sinh, so if we pull out a negative 1, what we'd end up with is e to the x minus e to the negative x, because these two would both change signs, and then I just reordered them, all over 2, but what we have right there is exactly the opposite of the hyperbolic sine. By definition, it's just the opposite of, and then of course this piece is the hyperbolic sine. So we have just proven that f of negative x is equal to negative f of x, and that means therefore f of x equals sinh of x is in fact odd. It is an odd function. Let's clean up our language. Is an odd function. And there's our proof. Okay, so turns out that hyperbolic sine is an odd function. Let's take a look at another identity. So this is an identity that we actually talked about when we talked about the graphical connection of these hyperbolic functions to the unit hyperbola. And I won't spend any more time going over that, but we can prove this using the exponential forms as well. And so I don't have them up on the screen, but let's just write them here. So the hyperbolic sine is defined as e to the x minus e to the negative x over 2, and the hyperbolic cosine of x is e to the x plus e to the negative x over 2. And so if I want to prove this identity, well, let's just start with hyperbolic cosine squared minus hyperbolic sine squared. And let's prove that that is in fact equal to 1. So if we take the hyperbolic cosine in its exponential form, e to the x plus e to the negative x over 2, and then we subtract the hyperbolic sine, e to the x minus e to the negative x over 2, and we square each of those, so hyperbolic cosine squared minus hyperbolic sine squared. And what we're looking at here is just expanding some exponential functions. So if we expand these out, we're going to get e to the x minus e to the negative x squared over 4, and I'm going to expand that on the next line, e to the minus x, e to the negative x squared over 4. And expanding out that numerator, we get e to the 2x, and then we get minus 2 times the product. So e to the x, e to the negative x, plus e to the negative 2x, minus e to the 2x minus 2. I just noticed I carried a negative down when it should have been a plus. So it makes that a plus right there. So let's fix that. E to the 2x, going back to my expansion of e to the x minus e to the negative x squared, e to the 2x minus e to the x, e to the negative x, plus e to the negative 2x. And this is just all over 4. And so now we just are going to simplify and distribute this negative here and simplify. And I just want you to notice that when we multiply e to the x and e to the negative x, I wrote it out on this line so we could just talk about it. When you multiply e to the x times e to the negative x, you get e to the 0, which is 1. So this whole term actually just becomes 2 because each, and as well as this one becomes a negative 2. Okay, because when you multiply those together, you get e to the 0. All right, so we have e to the 2x plus 2 plus e to the negative 2x minus e to the positive 2x minus 2 plus 2 minus an e to the negative 2x all over 4. And check this out, e to the 2x minus e to the 2x, e to the negative 2x minus e to the negative 2x. 2 plus 2 is 4, and we have 4 over 4. And it turns out that that is, of course, 1. And so therefore, we have just proven that the hyperbolic cosine squared minus the hyperbolic sine squared is, in fact, equal to 1. And so there are 2 quick proofs using the exponential expansions of our hyperbolics. Okay? Now, this one, again, was a it was a result of the way these hyperbolic functions are connected to the unit hyperbola, but we can also prove it in its exponential expansion. Okay, so we have a set of identities that come out of these hyperbolics. Similar to how we have a whole slew of trigonometric identities, we have a whole slew of hyperbolic identities. And so here are some of them. The even and odd identities, the hyperbolic sine is an odd function, which we proved. The hyperbolic cosine can be similarly proved to be an even function. So hyperbolic cosine is an even function. If you also think about their graphs, and I'm just going to do like a very rudimentary graph, but the hyperbolic sine has this sort of shape, and the hyperbolic cosine has this sort of shape. And so you can also see that even and oddness in the shapes of their graphs. The hyperbolic identities, and again, these come from that connection to that unit hyperbola, right? Our unit hyperbola with that shape. These come from that connection to the unit hyperbola, but the hyperbolic identities also proven in their exponential forms. Cosh squared minus sinh squared of x is equal to 1, and then 1 minus the hyperbolic tangent squared is equal to the hyperbolic secant squared, and the hyperbolic cotangent, I just noticed when I typed this, I lost the squared, so the hyperbolic cotangent squared of x minus 1 is equal to the hyperbolic cosecant squared. Okay. And then we have some addition identities as well down there at the bottom. And so all of these can be proven using the exponential forms, similar to how we proved 2 of those identities just a minute ago. And they're, it's nice to go through those proofs because it helps us to remember these hyperbolic functions. And while we might not see them a ton, we might not use the hyperbolic functions as much as we actually use the trig functions. Moving forward in this calculus course as well as into your future calculus courses, having some knowledge of these hyperbolics is a really useful tool. It's a tool I always like to put into my students' toolboxes, their brains. I like to go through these and I like to talk about them and their connections to the unit hyperbola because they are very useful. Okay, so now that we have gone through another quick review of what the hyperbolics are, as well as some identities, let's get into some calculus with these functions. So how do we take their derivatives? Well, we don't have to do anything really new to come up with what the derivatives of the hyperbolic functions are because we know how to take derivatives of exponentials, and our hyperbolics are defined as exponentials. So if we want to know what the derivative of the hyperbolic sine is, we should start by looking at its exponential expansion. So what is the derivative then of e to the x minus e to the negative x over 2? And that is simply, that's a 1/2, it's a constant 1/2, so we could just take the 1/2 out and then say what's the derivative of e to the x minus e to the negative x. And exponential derivatives are fun, quick derivatives. E to the x is just e to the x, and then minus the derivative of e to the negative x is going to be negative e to the negative x, because we have to take the derivative of the negative x, so we get that -1 right there. And so this becomes 1/2 e to the x plus e to the negative x. And check that out. E to the x plus e to the negative x over 2 is exactly the way we define the hyperbolic cosine. And so it turns out that the derivative of the hyperbolic sine of x is equal to the hyperbolic cosine of x. And that is a very fun, cool result. Think about how the trig functions are related. The derivative of the sine of x is the cosine of x. And so the derivative of the hyperbolic sine, sinh, is equal to cosh, the hyperbolic cosine. So what do we think? Would we suspect that the derivative of the hyperbolic cosine of x will be negative sinh, since that's the relationship for the trig functions? I don't know, but I know a way we could figure out. So let's do it. So let's figure out what is the derivative of the hyperbolic cosine. So the derivative of the hyperbolic cosine, again, we would say, well, how would we define how is the hyperbolic cosine defined as an exponential function? And it's e to the x plus e to the negative x over 2. And so this is going to be a very similar derivative. Slight sign changes, so we pull out the 1/2 and then look at the derivative of just e to the x plus e to the negative x. And that's just going to be 1/2 e to the x plus a negative e to the negative x, which is let's actually write it, e to the x minus e to the negative x over 2. And that is not a negative, but exactly the sinh. So that is actually the hyperbolic sine. So notice here that when we took the derivative of the hyperbolic cosine, we got back the hyperbolic sine. Again, an interesting and handy result. So similar, right? Similar to the way the trig derivatives work, but notice that this does not have a negative sign on it. Like if we take the derivative of the cosine of x, we get negative sine of x. That is not the case here. The derivative of the hyperbolic cosine is actually the hyperbolic sine. So the derivative of the hyperbolic sine is the hyperbolic cosine, and the derivative of the hyperbolic cosine is the hyperbolic sine. Okay, let's do one more, and then I'll leave the other 3 for you as exercises and practice. So how do we take the derivative of the hyperbolic tangent? Well, the derivative of the hyperbolic tangent, we could go to its exponential. So we could use exponentials. So we could use exponential form. But better yet, we just proved, using exponential forms, we proved the derivatives of sinh and cosh. So let's erase that out of there. And instead, since we already know the hyperbolic sine and the hyperbolic cosine derivatives, all the other 4 hyperbolic functions are defined in terms of those. So for the derivatives of all the other 4, let's just use the definition of the hyperbolic tangent of x in terms of sinh and cosh. Okay? So we had some options here, but I would prefer to work with the more simplified version, since we already proved what these derivatives are, and they are exponentials. Sinh and cosh are exponentials, but we've already proven what their derivatives are. So if I use that, this is a quotient. Burp, burp. So we just have to apply a quotient rule. So the derivative of a quotient is the derivative of the top, but the derivative of sinh is cosh times cosh, the bottom, minus the derivative of the bottom, but that's just sinh, times the top, all over cosh squared, all over the bottom squared. So notice what this was right here. I jumped right into just the actual derivative. I just wrote that backwards, sinh of x, and this was the derivative of cosh of x. Okay. So that's where these two came from. I jumped right into it and kind of whizzed through there. All right, so we end up with the hyperbolic cosine squared minus the hyperbolic sine squared all over the hyperbolic cosine squared. But this is a hyperbolic identity. Hyperbolic identity right there. Hyperbolic cosine squared minus hyperbolic sine squared is simply 1. This is a hyperbolic one we proved. So this is a hyperbolic identity, so this is just equal to 1 over the hyperbolic cosine squared, which is the hyperbolic secant squared. And there's our proof. The derivative of the hyperbolic tangent, and again, notice the connection to the trig derivatives. The derivative of the hyperbolic tangent, I'm trying to write and talk and flipping letters around, the hyperbolic tangent of x is equal to the hyperbolic secant squared of x. And we've proven it using quotient rule and the two derivatives of the hyperbolic sine and hyperbolic cosine. So there are our proofs from all three of the first three hyperbolic functions. And we can prove the other three hyperbolic functions derivatives as well, simply using how they are defined in terms of sinh and cosh and using quotient rule. Okay, so worth freezing the screen here and getting these down. These are going to be derivatives we're going to need to know. We need to add these into our bank of useful derivatives. Derivatives of the hyperbolic functions are ones we need to know. So obviously we've proven the first three, sinh, cosh, and tanh, and you can prove as an exercise the last three. Okay, so let's actually take some derivatives. Just using what we now know about those derivatives, let's do a couple examples to round out this video on hyperbolic identities and hyperbolic derivatives. So if I want to take the derivative of the following functions, so find the following derivatives, find the derivatives of the following functions, maybe would be a better way to say that, but find the derivatives. I tried to set that up ahead of time. Find the derivatives of the following functions. All right, so let's get in here and let's do it. So if we want the derivative of x squared times sinh of 3x, and you do have to recognize, right, like you want to definitely recognize that h there, that we're not talking about a trig function, we're talking about a hyperbolic function. So let's make sure that when we come across a hyperbolic that we do recognize it and we don't just think, hey, that's weird, wonder why they typed in or why Katie put in a h on my trig function. We got to recognize those are the hyperbolic functions. So we're taking the derivative, it's a product, and we got a little bit of a nested function here with the 3x, so we'll have to use chain rule, and we're just going to do it. Let's just get in here. So this is going to be 2x times the hyperbolic sine of 3x plus the derivative of the hyperbolic sine is hyperbolic cosine of 3x, but then I have to multiply by 3 because of chain rule, and then x squared to round out the product rule. And so this ends up being 2x sinh of 3x plus 3x squared cosh of 3x. And we could, I guess, factor out an x, but I'm going to leave it just like that. And there we go. All right, let's do another one. Let's do one where we've got some nesting happening. We've got chain rule, repeated chain rule here because we have 7x squared inside of a hyperbolic tangent, all of that inside of a hyperbolic cosine. So we'll have to peel away the layers. We got repeated chain rule here. And we want to just work our way through that, taking the derivative. So dy dx, the derivative obviously of the outermost function, cosh is going to be sinh, so hyperbolic sine of hyperbolic tangent of 7x squared. Then we have to multiply by the derivative of the next layer, the next the middle function, I guess, in this case. So the derivative of the hyperbolic tangent is the hyperbolic secant squared of 7x squared. And then we have to go one layer further and we get 14x. Now, not a whole lot to do here in terms of simplification, so I'm not even going to rewrite it. I'm going to say, there we go. There's our derivative. Okay. Let's go ahead and take a look at one where we do a little more with the derivative. So what if we wanted to find the equation of the tangent line to the hyperbolic sine of 1 minus x squared? So anytime we want the equation of a tangent line, we know we got to start with the derivative because we need to find the slope. So we need to find the derivative so that we can find the slope. So let's start with the derivative. So the derivative here, dy dx, is going to be the derivative of the hyperbolic sine is the hyperbolic cosine of 1 minus x squared. And then we have to multiply by a negative 2x because we have to take the derivative of the inside. So the derivative ends up being negative 2x times the hyperbolic cosine of 1 minus x squared. And there's the derivative. Okay, now we want to find the equation of the actual tangent line. So we have to think about what is the point that we're going through. We know that we go through 1, so the point would be 1 and what? Well, we got to plug that in. So y of 1, since we don't have function notation, I'll write it that way. Y of 1, what is, let's just go to black here, y of 1 is the hyperbolic sine of 1 minus 1 squared. Okay, well, that's 0. So this is the hyperbolic sine of 0. So how do I figure out what the hyperbolic sine of 0 is? Well, there's a couple of things that we could do. We could think about the graph, and if you remember the graph goes through 0. So at 0, we're at 0 for an output value, but what if it wasn't 0, right? And we couldn't do it graphically. How would we do this? Well, we would go to its exponential expansion. This is e to the 0 minus e to the 0 over 2, which is 1 minus 1 over 2, or 0 over 2, or 0. So remember, anytime you need to evaluate a hyperbolic function, you can go to its exponential expansion and plug into the exponential and use what you need to use either to estimate on a calculator or to come up with the exact value in exponential form. So this is actually 0. So we know that we're passing through the point 0. Now we need the slope. And so let's go ahead and figure out what dy dx is at x equals 1. So we're going to plug in 1, negative 2 times 1 times the hyperbolic cosine of 1 minus 1 squared. So we end up with a negative 2 times the hyperbolic cosine of 0. And so once again, we're at that point where we're having to evaluate a hyperbolic function. And so if you remembered the graph, and I know we went through that on the other video, but if you remembered the graph of that hyperbolic cosine, the hyperbolic cosine looks like this, and it passes through 1 when x equals 0. So if you remembered that, you could utilize that. But again, in practice, what we tend to do when we want to evaluate a hyperbolic function is we go to its exponential form. So this would be e to the 0 plus e to the negative 0, which is e to the 0, over 2. And that, of course, is just negative 2 times 2 over 2, which is 1. So there's the hyperbolic sine value as 1 at 0. And the slope is negative 2. Okay, so we know that our slope is 2. So now we actually put that together and write the equation. So y minus 0 equals a negative 2 times x minus 1. And y would be negative 2x plus 2 would be the equation of my tangent line to this curve at that point. Get that all on the screen at once. There we go. And I'm going to end the video there, and we'll pick up and talk about the inverse hyperbolics on the next video.